Welcome back, everyone. In this lecture, we're going to build on uh, or build on our model for electromagnetic uh, electromagnetic waves, photons in a cavity that we looked at last time, black body radiation. Um, and we're going to build on this looking at a new model for solids. So up till now, we've been using the Einstein model for solids, where um, we've been modeling the molecular motion uh, in the lattice as just a collection of independent simple harmonic oscillators. But in reality, the vibration of the molecules in a lattice is probably not independent. That if you have a molecule vibrating over here, it's going to wiggle its neighbor, and there's going to be some interplay between those molecules. So instead of treating them as independent solids, we're going to make a model that looks rather like the model we just used for photons in the electromagnetic field. So instead of modeling the motion of individual molecules, what we will be looking at is um, excitations, wave modes in our solid. So very much like the electromagnetic field inside our cavity formed these standing waves. We're going to model the motion of the atoms in our solid, or the molecules in our solid, as sort of a wave um, with a lowest order mode. If we look at the text or the figure in your text, that you've got a lowest order mode here where all of the molecules are vibrating sort of in the same direction, and then the second lowest mode here where you've got a complete wave across your solid object, and then the n equals 3 mode, and so on. So that what we're doing is in fact very much analogous to what we just did with black body radiation, with a few differences. So first of all, we're not dealing with light, we're dealing with the motion of molecules in a solid. So the relevant speed is not the speed of light, but the speed of sound through our solid. We're going to make the approximation that the speed of sound is isotropic and that it's frequency independent, and neither of those things is necessarily true for all solids, but we're not going to make the most complicated model of a solid here. We're just going to do a little bit better than we did with the Einstein solid. The second complication is that, or the second change from the photon case for the excitations in a solid, is that the waves can be not only transverse, like in the electromagnetic case, but they can be longitudinal, so that the vibrations can be along the wave, not just perpendicular to the wave. And that leads to 3 polarizations rather than just the 2 polarizations. So there will be a factor of 3 hanging out in the front as opposed to a factor of 2. And again, we're going to ignore the possibility that the sound speed for longitudinal vibrations is different than the sound speed for transverse vibrations. And then finally, the excitations or the waves have a smallest possible wavelength, or the largest number of a largest frequency in our in our solid, which is a different condition than for photons, right? So for photons, there was a lowest wavelength that was allowed in a cavity, but you could do the upper limit all the way to infinitely small wavelength or infinitely large frequency. But for, and I'm going to borrow his, but for solids, where we have individual molecules, the largest frequency or smallest wavelength that makes sense to talk about is the one where every other molecule, every other atom is vibrating in the opposite direction. Beyond this point, it doesn't really make sense to think about wiggles happening between the molecules. So when we talk about the excitation of phonons as opposed to photons, so phonons would be mechanical vibrations in our solid, essentially sound waves. We're exciting sound wave particles, sound wave excitations in our solid rather than light wave excitations in a vacuum. We'll have to take into account these effects, but in many ways the calculations look very much like they did for the case of light. So in particular, these modes will have an energy associated with them, which is h Planck's constant times the frequency. In this case, that will be Planck's constant times the sound speed over the wavelength. And breaking those up into allowed modes, numbered by n from 1, 2, 3, 4, 5, etc. This will be Planck's constant times the sound speed times mode number over twice the length of the cavity, where n here is the absolute value of our three-dimensional n vector, right? So in the case of the lowest allowed mode, that would be basically, 1, n equals 1, and in each of the directions, and so on. So given this energy distribution, there would again be a Planck distribution for phonons, which would be applicable here, which again is 1 over e to the energy over kT minus 1. This would be the expected or average or thermal average occupation of each excitation mode, where the energy is given up here by this. And so if we wanted to find the total thermal energy, we would have to sum, well, there'd be this factor of 3, because again, the 3 polarizations, and then we're going to sum over nx, ny, and nz. The energy of that mode times the Planck distribution for that given energy. Now again, unlike the electromagnetic case, these sums have an upper limit, right? They go from 1 to an n max, and the upper limit then for nx, ny, and nz, if we have a cubical a cubical volume, is going to be so the max allowed n for each of these is going to be the cube root of the total number of molecules. And so we would be in, this sum is inherently a sum over Cartesian rectilinear modes. And when we did this calculation for photons, we converted to spherical coordinates. But technically, we should be doing this in Cartesian coordinates. The problem is integrating this Planck distribution in Cartesian modes, x, y, z, is super ugly because the energy here depends on the square root of the sum of squares of x, y's, and z's, and this is going to get ugly. All right, so to allow this, I mean, you can do this numerically, obviously, but there is an approximation which Debye came up with called Debye, or called the Debye theory, and that's what we're going to use here. And Debye's solution was to go ahead and integrate over spherical coordinates. So do that same 1/8 of a sphere that we saw before in nx, ny, and z space, right? Now our real states here, if we look at this diagram from the book, they are going to be arranged along those that grid, right? And if we had a cubical solid, then we should be just integrating over that cubical solid. But as I said, this is a much more convenient integral to do in spherical coordinates. So what Debye's solution was, is to go ahead and integrate over this 1/8 of a sphere, but to adopt as the limits of our integration the sphere that gives us the same number of particles, the same volume, essentially, in n space. So that we have the correct volume n in that n space, so that we would then be saying that our maximum n value would be the n value that gave us the correct volume n. So we're going 1/8 of a sphere whose volume is 4/3 pi n max cubed, and that 1/8 of a sphere has to have a total volume n, which we can, let's see, the 4 and the is going to cancel all but a 2 down there, and so that's going to give us a pi over 6 n max cubed is our n, or in other words, that the maximum little n, the maximum mode number, would be 6 times the total number of particles divided by pi to the 1/3 power, or the cube root of that. Now, this approximation works interestingly, it works at both the high temperature limit and the low temperature limit. It doesn't work so great at intermediate temperatures, but at the high temperature limit, or at the low temperature limit, then those outer modes where the difference between our square volume and our spherical volume are most important, well, all of those modes are exponentially suppressed because the temperature is low. All right, so it doesn't really matter what the edges look like. Those modes aren't going to add significantly anyway. And at high temperatures, it turns out that it's only the total number of modes, it turns out that it only depends on the total number of modes, not their configurations. And so since we kept the volume correct, it was fine, or it's fine at the high temperature limit. All right, so if we go back now to our calculation, what we're going to do is we're going to convert this triple sum to an integral in spherical coordinates again. So our thermal energy is that factor of 3 out front, and now we're going to integrate from 0 to the n max we just calculated in our, again, radial dn coordinate, and then integrate over the angular coordinates 0 to pi over 2 d theta, and 0 to pi over 2 d phi. So again, those are the angular coordinates for our 1/8 sphere. And then the usual volume term, n squared sine theta. And finally, the thing that we're summing, mode energy over mode energy times the Planck distribution. So e to the minus energy over kt minus 1. Integrate that in dn. The angular integrals, so sine theta, d theta, and d phi, this angular integral gives us a factor of pi over 2. And so that pulls out to the front. Our energy is 3 pi over 2 times the integral from 0 to n max of, go ahead and put in our mode energy, hc squared over, or h sound speed over 2L, times n, which gets added to the n squared to give us an n cubed. Again, e to the h sound speed over kt minus 1. Yes, this is energy here down on the bottom. So let me just write this as 1 over e to the h sound speed n over 2L kt minus 1 in dn still. And we're going to do the usual thing, convert that so that e to the x is an e to the x integral. So our x has to be Planck's constant sound speed n over 2L kt, which means that our n then is equal to 2L kt over Planck's constant times the sound speed times x. And we can convert that L to 1/3, or the cube root of volume. So this is 2 kt over hcs times the cube root of volume times x. Our x max here would just be h times the sound speed times our n max over 2L times kt, and our n max, where our n max is given by this, so this is h times the sound speed over 2 kt times 6n over pi and volume to the 1/3 power. And we're going to define that as the so-called Debye temperature over T, where this Debye temperature is a characteristic temperature for our distribution here. We can then, given this, calculate a dn here, which is 2 kt over Planck's constant times sound speed times volume to the 1/3 dx, and plug all this in, plug all this into our integral equation, 3 pi over 2, and the integral from 0 to x max of Planck's constant times the sound speed times 2 over volume to the 1/3 times 2 kT over Planck's constant and the sound speed cubed times the volume. So this is the n cubed term. This is our term out in front where we've just converted the L to a cube root of volume. And now we have a x cubed over e to the x minus 1, and the dn gets converted like this, so that's 2 kT over Planck's constant times the sound speed times volume to the 1/3 dx. And now a bunch of things can cancel. This volume to the 1/3 cancels with that volume to the 1/3. This 2 here cancels that 2. The Planck's constant times the sound speeds cancel. And so what we're left with is, let's see, the same 3 pi over 2. But now we can pull out 2 cubed and 8 times a kT cubed over Planck's constant times the sound speed cubed times the volume. And then there's an extra kT from the dn term, and the integral from 0 to x max of x cubed over e to the x minus 1 dx. And as is usual with these things, this integral is going to turn out to be one of those things you either look up in a table or integrate numerically. But again, look in the back of the text in Appendix B. He goes through how to integrate some of these. So, whoops, don't lose that. Off we continue our calculation here. We can convert this x max to the TD over the Debye temperature over T. And the 8 over 2 gives us 4 times 3 gives us 12. So this is 12 pi out in front, kT to the 4th. Again over Planck's constant and the sound speed cubed times our volume term times the integral from 0 to TD over T e to the x minus 1 dx. And let's take a look at that Debye temperature. So the Debye temperature is Planck's constant times the sound speed over to K times 6n over pi times the volume to the 1/3. And so if we cube both sides, the Debye temperature cubed is HCS cubed over 8k cubed times 6n over pi times volume. So a bunch of the terms up here can be written in terms of the Debye temperature. If we take this 12 pi kT to the 4th over Planck's constant sound speed cubed times volume, and multiply, or take that term, just this term. So we're just going to take this constant grouping out in the front. If we multiply that by TD cubed over TD cubed, and we still get the 12 pi KT to the 4th over h sound, or sound speed cubed, times 1 over TD cubed on the bottom, and TD cubed over here, so h sound speed cubed over 8k cubed, 6n over pi times volume, and a bunch of things are going to cancel here. The pi's cancel, the Planck's constant terms cancel, and a bunch of these constant terms cancel, and what we get out of this is rewriting our integral 9n k t to the 4th over the Debye temperature cubed times the integral from 0 to Debye temperature over t, x cubed over e to the x minus 1 dx. Now, that has no analytic solution. We could integrate it numerically, but for high temperatures, if we examine the high temperature limit, such that the temperature is well above this Debye temperature, then the upper limit will be small, and so our x is always going to be a number much, much less than 1, in which case we can approximate e to the x as 1 plus x. And so then our integral for high temperatures is just going to be 9n kt to the 4th over Debye temperature cubed times the integral from 0 to TD over t of x cubed over 1 plus x minus 1 dx. That's just going to give us 9n kt to the 4th over Debye temperature cubed. The integral from 0 to Debye temperature over t of those cancel, and then we've got x cubed over x, so that's x squared dx, and we can integrate that pretty straightforwardly. This is just going to give us 9n kt to the 4th over td cubed times 1/3 td over t cubed, and the 9 cancels with part of the 3 and gives us a 3. The TD cubed cancels with the TD cubed. And the T cubed cancels all but one of the T to the 4th. And so we're left with 3nkt, which is in fact the equipartition solution. That we got for the Einstein solid. So at the high temperature limit, the Debye theory, or the Debye approximation here, gives us the same result that we had already run across. But now we have the opportunity to take that to low temperatures, which the Einstein solid did not do very well with. So for low temperatures, for T much, much less than the Debye temperature, then the upper limit is large on this integral. And so we might as well just let it go to infinity. And integrate all the way out to infinity. And then our integral then just becomes the integral from 0 to infinity of x cubed over e to the x minus 1 dx, which again, if you look it up in a table or go to the back of the book and dig through the various tricks to get here, gives you pi over 4 times 15. And so our energy for low temperatures, 9 nkt to the fourth over Debye temperature cubed times pi to the fourth over 15. So that gives us 3/5 pi to the fourth nkt to the fourth over Debye temperature cubed. And if, for instance, we wanted to calculate the heat capacity for our solid, that's du dt. That's going to be, well, it goes as t to the fourth, so the fourth is going to come down and give us 12 pi to the fourth over 5 T over Debye temperature cubed times nk, or in other words, proportional to T cubed. So the temperature dependence of solids in the heat capacity would be expected to go as T cubed in the low temperature limit. And indeed, here we can see some actual experimental data for gold, silver, copper, showing indeed that we get T cubed behavior at low temperatures in the heat capacity. Notice that note that this is just the heat capacity due to the vibration of our molecules. If, like those things that we just looked at, gold, silver, copper, if we were actually looking at metals, most conductors like that have that free electron cloud in them, and so when we talked about the Maxwell equation or Maxwell distribution, we looked at the heat capacity for free electrons and found for our free electron gas that the heat capacity could be written as pi squared over 2 n k squared T over the Fermi temperature or some constant gamma times T. So there's a linear term in the CV from the electrons and a T cubed term in the CV from the molecules, and so the total heat capacity would be the sum of those two, a linear term plus our our cubic term, 12 pi to the fourth over 5 T over Debye temperature cubed nk. for intermediate temperatures between the much less than Debye temperature and much greater than Debye temperature. So if we have temperatures of order D or Debye temperature, then you would have to do some numerical integration of our integral. And indeed, if what you're really wanting to know is predict his heat capacity, then it's a little bit more accurate to go ahead and do that differentiation under the integral sign, which would give you a slightly different integral to integrate over. 9nk t over td cubed times the integral from 0 to td over t of x to the 4th e to the x over e to the x minus 1 squared dx, and integrating this numerically to whatever value of t over the whatever your value of temperature is with respect to the Debye temperature would give you, as accurate as this theory is going to get, an approximation of the heat capacity. All right, there we go. In the next little mini lecture, the last little mini lecture here, we're going to look at the Bose-Einstein condensation, but I'll go ahead and put that in a separate video.